Hello, welcome to our video on derivatives of exponential functions. I'm expecting this to be a bit of a shorter one, but still not easy. Well, it might start off a little easy, but we'll mix in some chain rule, and that makes things a little more interesting. So here's what I'm referring to as easy. The derivative of the natural exponential e to the x. So taking the derivative of e to the x, I say this is easy because turns out it's its own derivative, which is fascinating. But e to the x describes its own rate of change at every point. So that's pretty cool. But we will make this more complicated by throwing in chain rule. Find f prime of x for f of x equals e to the x to the 4 minus x. So this is chain rule because I have x to the 4 minus x as the input of my e to the x function. So in may not be the most intuitive word here, but it's the input. Right, this is getting plugged into an e function. It's getting plugged into an e to the x. It's just that x is no longer the input, but this whole thing. So we do chain rule because this is derivative of a composed function. Well, the derivative of the outside portion, derivative of the e to the x function is itself. So that's what I get here. I just get this thing back. It's its own derivative. And remember, with chain rule, you leave this inside part alone in this early step. So I'm not yet touching the x to the 4 minus x, but just stringing it along. So I've taken the derivative of this outside function. It's just this thing itself. Then times the derivative of the inside, or in this case, what we have in the exponent. And that's it. Next, let's use some different wording here. We're taking the derivative of the square root of e to the x. So this time my inside function is e to the x. It's inside the square root. It's the input of the square root function. However, I want to start this a little differently. I'm going to take this one with two different approaches. Or let's call this method. So first method, I'm going to show you two ways to do this. First method will be to rewrite this expression. I think this is a little easier. Yeah, let's write it like this. So parentheses, e to the x, taken to the 1/2 power, because that's the same thing as a square root, remember? And this is convenient because I can use exponent rules. When I have a power to a power, you multiply those powers. So I haven't even taken the derivative yet. I'm just rewriting that expression. So multiplying x and 1/2. This is just derivative of e to the 1/2 x. Now this is chain rule. It's just a little different than what I said at first. In this case, e is the outside function because we're plugging in 1/2 x into an e to the x function. Right, so remember chain rule, you're taking the derivative of the outside, except the input is a little different, but you just leave it alone. Derivative of e to the x is itself. So I just write e, but it's not to the x. Remember, we have a different input, 1/2 x. So remember in the chain rule formula, this is that f prime of g of x part, leaving that input alone, plugged in there, the 1/2 x. And then this is times the derivative of that inside part, the derivative of 1/2 x, which is just 1/2. So I'll write that first, 1/2 e to the 1/2 x. And let's get back to the form that it was written in before. Remember the steps we did at the start? E to the 1/2 x is the same if you go backwards as square root of e to the x. So this is the form I'm choosing to leave it in. So the derivative of the square root of e to the x is just 1/2 times the square root of e to the x. That's the first method, where I just rewrote the original expression using exponent rules. Second method, I could do chain rule right away, with e to the x being inside the square root function. So that outer process is taking a square root. And let's see if we get the same answer. We should, otherwise something's wrong. So derivative of the outside. Well, remember that I can rewrite this as x to the 1/2. But again, we do have a different input here. It's not just x, but the input is e to the x. We just string that e to the x along for now. But I will do a power rule bringing the 1/2 down. It's just not x in here, but e to the x to the 1/2 minus 1 power, or negative 1/2 power. So I've taken the derivative of the square root, essentially, but leaving this e to the x alone plugged in there. And now we multiply by the derivative of e to the x. That's chain rule. Well, e to the x is its own derivative. And now we'll simplify. So we are getting the 1/2, same as we did with that first method, so that looks promising. But it doesn't quite look the same yet as our old answer. But let's rewrite it like this. Times e to the x to the 1. Same thing as e to the x. But now I can do exponent rules. I have these exponentials being multiplied, and it's this same quote-unquote base. It's just the whole e to the x. What I'm getting at is that I can add these two powers using exponent rules. And that becomes 1/2 e to the x all to the positive 1/2. And that's 1/2 times the square root of e to the x, which is the same answer that we got right up here, that first method. So it works. I just did two different approaches for the same thing. Last problem, but it's a bit of a long one. So if our function y equals e to the x times square root of 5x minus 17. So this is the input being plugged into the e function. So the derivative of y with respect to x, dy dx. Moving a little faster now. So I'm doing chain rule because I have this expression being plugged into the e function. So I'm taking the derivative of the e part, but leaving this inside expression alone for the time being. Remember, the derivative of e, or e to the x, is itself. So that's just repeating this thing back. But now I multiply by the derivative of that inside expression, that exponent. So there, I just did chain rule. Well, notice this is not the easiest derivative in the world. Notice that it's a product. Right, I'm taking x times this square root. So that right there is a product rule. I'll copy this first part. And I'll need my parentheses because this is going to be a pretty big expression. So times this whole derivative. Well, I take the derivative of the first piece, derivative of x is 1. Times the second piece, then plus x left alone, times the derivative of this square root portion. So I just did product rule there, the derivative of, well, this product. Well, notice that this is actually not the simplest derivative in the world either. This is also a function composition, where I have the expression 5x minus 17 being plugged into a square root. That's function composition, so that little derivative part is going to be a chain rule. So here, copy my old stuff. Okay, don't need to write the times 1 anymore. Plus x times this derivative. So in this case, my quote-unquote outside function is a square root, or taking something to the 1/2 power. So I perform the derivative of that power rule, bring the 1/2 down, times leaving this inside expression alone. To the negative 1/2, I subtracted 1 from 1/2. So that's the first part of chain rule, taking the derivative of the square root on the outside, and then you multiply by the derivative of the inside, which is just 5. Derivative of 5x minus 17 is just 5. All right, that's a little challenging. The good news is we're done taking derivatives in our steps. Now we're just looking to simplify. Okay. Well, let's look at our numerator. We're going to have a denominator here thanks to this negative exponent, and we also have a 1/2 anyway. So let's organize this neatly. In the numerator, I have a times x and a times 5, so 5x. And in the denominator, I have a 2, and this square root being moved down. Again, thanks to that negative exponent. Now we can simplify this a little more by finding a common denominator that will allow me to write this, bring this together as one expression, one fraction. So that's nice to do. And I got this problem from Pearson, by the way, and that's how they got their final answer. So I'm following the way that they want the answer. So I'm not just wasting your time. In order to bring these things together, I need a common denominator, like I said. Well, our old denominator over here is just 1. I'm dividing by 1. So we'll just introduce this whole other thing. So I had this before, and now I'm multiplying by that new thing I added. So let me highlight. This is the new stuff that I threw in, so that I can get a common denominator. Right, we have that same denominator over here. So this part does not change. Well, this is pretty nice. Notice that I'm multiplying this square root by itself. So the square root actually goes away up there. And don't forget this times 2 that we have. So a 2 times, now no more square root. And I'm bringing this all together now since we have the same denominator. So plus 5x. All over that common denominator. And then we're almost done with this. Okay, I can distribute this 2. Here it gives me 10x minus 17 plus 5x. Oh, excuse me, that's wrong. Minus 34. 17 times 2. And I have these like terms, these x terms, which can come together. And then we'll be done with this. And by the way, I was slightly incorrect when I said this is the last problem. But we're almost done here. I did want to show you one more little thing. But yeah, that's a challenging problem. So, real quick, this little lesson is called Derivatives of Exponential Functions. So far, we've actually only looked at one type of exponential function, e to the x. But there are others out there, like 2 to the x, 3 to the x. So let's talk about those. We tend to not focus on them as much. This is certainly the most important one. But I want you to see the other kind. So remember, the base of an exponential function, we call it a. We like for it to be positive, but not 1. Then the derivative of a to the x. Well, so far it looks kind of similar to what we saw before with e to the x. But you multiply by natural log of a. So this is the more general formula for any exponential. Let's just look at an example or two really fast. So the derivative of the function 2 to the x is itself, but times natural log of 2. And now if this formula is true, it should work for e as well, because e is a positive number and not 1. It's about 2.7. So let's try derivative of e to the x using this formula. Get e to the x times ln of e. But ln of e is 1. Because remember, ln, natural log, is really log base e. So log base e of e, that cancels to 1. So we get our old formula like we should. Okay, well, next time we'll talk about logarithmic functions, especially ln in particular, taking its derivative. So see you then.